Our first speaker is Andrew Lenton. He's going to talk to us about ocean liming.
Okay, you guys are legends for staying to the end. Well done. All right. So, of course, I'm going to thank, because we're in the last session, I do want to thank the organisers of this meeting. It's been excellent to get together as a community. So today I'm going to talk about, assessing CDR through global and regional ocean alkalinization. I'm going to focus on high and low emission pathways. And in some ways, this very much follows on from the talk Phil gave this morning. This is the kind of downstream, in some ways, is the ocean side of using the enhanced weathering. And it touches on some different talks that were also presented in the enhanced weathering session. So in this meeting we've talked a lot about warming and 1.5 degrees and it's very important, and we know that, and we can see, especially up in the Great Barrier Reef, we know we're bleaching annually, we're getting lots and lots of problems. But something we haven't touched on, and we've kind of just touched on briefly, I should say, is ocean acidification. And ocean acidification is one of those things where, while the upper ocean may be somewhat reversible, the ocean itself is not. It takes many, many, many centuries, thousands of years in order to actually start to return to what it was. So it's hanging around a long time. So what I've just really briefly put it up here is just, I know this is a very broad audience, so I've just kind of put a schematic of what ocean acidification is, and I'll step through it super fast, and most of you know it. But it really is around, pardon me. So it really is around this idea that as we put more CO2 in the atmosphere, more is taken up by the ocean. It's this kind of feedback. It's this idea that the ocean pays an ecosystem service for us. And as it goes in, it causes a decrease in carbonate ion concentration and an increase in hydrogen ion concentration. So this is the decrease in pH. It's defined this way, decrease in pH. It's a negative log, and this is the decrease in the carbonate. And these are the two things that are often referred to as ocean acidification. And this is particularly important for calcifying organisms, calcitic, aragonitic, high mag calcite organisms. But the pH is equally as important because that essentially deals with fecundity, it deals with sensory impacts. There's a whole bunch of things in the marine system, and we're only just starting to get a handle on what these implications may be longer term. So I know that's a real 101, but I think it's helpful still to step through this. So I'm particularly interested in AOA, or as Phil Remforth was talking about, ocean liming, because of the fact that it actually directly addresses the ocean acidification as well as increasing the uptake of CO2. So again, what it does is it pushes the pH back up, it increases the carbonate ion concentration, increases the buffering capacity of the water, and of course it leads to the gradient between the atmosphere and the ocean being enhanced and more uptake. And for those that haven't done a lot in this space, it really is an enhancement of a natural process, one of the processes that we think has played an important role in the glacial interglacial cycles. So we're looking at ocean alkalinity addition. We're looking at under high and low emission pathways, 2.6, 8.5, and we're also looking both global addition in the ice-free ocean, but also the regional addition. So if we put it in some places, are they more efficient than others, and how does that play out? We're using a fixed addition of alkalinity, 0.25 petamoles. That's the number that comes from a paper very similar to a number that Peter Kohler used and David Keller used in a previous paper, sort of somewhat related to the shipping capacity. But it's not, I don't want you to focus so much on what the number is, just more the comparison between the regional and the global and the difference between the emissions pathways. And to do this, we're using an Earth system model. And this is an emission-driven Earth system model. So very similar to the CMIP-5, a little bit older class, but very similar. The only major difference from the Earth system models that most of you know about is we do have a limitation on the land of both nitrogen and phosphorus. So it's a little bit different. And it's a little bit coarser resolution, so it allows us to run faster. And so the experiments, 10 model runs altogether. As I said, high and low emissions pathway. We've seen that all this week. Like I said, we're doing it in the ice-free ocean. The AOA global is all the ocean. This is subpolar, the subtropics, and the tropics. And so obviously, when we do it just in the tropics, we're going to have a higher per unit area input of alkalinity, needless to say. And so, like I said, so it's 10 simulations. So we have the 4 different simulations under each of the emission scenarios. That's 10 simulations in total. Okay, so the first thing I wanted to show you, of course, is we want to check, when we're putting the alkalinity into the ocean. Now we actually, in our model simulation, we're actually seeing that. And what you're seeing here is at the end of the simulation, and what you can see is there's very little difference between RCP 8.5 and 2.6 in terms of the totally global change over that period. There is an increase, you'd expect that. It's very similar between 2.6 and 8.5, and you can see when we put it in globally, it's fairly diffuse. Subtropics, we can start to see it picking up. Tropics, you can see it picking up. So you see quite a different spatial pattern in where that alkalinity is going in. Okay, so let me move to some what I think are some really interesting results here. And what we looked at here are the changes in, what we're looking at is the atmospheric concentration over here. We're looking at in time, and I should say, and I'm sorry, I skipped over this, we start the alkalinity injection in 2020, and we go through to 2100. So that gives you some idea of the scale. So what we're looking at here are the differences over this period, 2020 to 2100. And what you can see here is under higher emissions, so this black line is RCP 8.5 with no alkalinity addition. Here it is with alkalinity addition, the same thing, 2.6, and again with alkalinity addition. And the first thing you can see is, first thing you should be able to see is that there's a larger uptake under high emissions than low emissions, very much in part to do with the gradient, the higher gradient between the atmosphere and the ocean. But interestingly, what I think is really interesting anyway, is that there's very little difference despite the fact the alkalinity is going in totally different places, there's very, very little difference globally where you put it in. It's happening so fast that in some ways the global carbon uptake is invariant to where you add the alkalinity, which I think is quite interesting. And again, we see, and so in some ways, the difference between there is almost insubstantive. But what's interesting is, so we get about an 82 petagram, 82 ppm change in the atmosphere, 53 in the atmosphere under lower emissions. But what you see here is it's the oceans doing the bulk of the work. In fact, what's happening is the ocean's taking up carbon under both of the scenarios, but actually the land is actually letting it out. And the reason is because we're getting a small cooling, we're getting a cooling associated with alkalination, and what that means, it's actually repressing both soil respiration and primary production, but primary production is in the land is in fact being repressed more. So that's why we get a small decrease in uptake going forward. So essentially, the take-home message here is invariant to where it goes and essentially abiotic processes in the ocean. It's just chemistry, no changes in the biotic, but on the land we're seeing biotic changes. Okay, let's look at the changes in surface mean temperature over the same period. Again, surface temperature here, 2 metre temperature, again, 2020 to 2100. The black lines again represent the control simulations and the colours represent the different places in where it goes. And what you can see here is despite larger uptake of CO2 under high emissions, you actually get a larger cooling under low emissions than high emissions, which is really, really fascinating. Again, very little difference as you'd expect between the simulations, but you can start to see here under the lower emissions, you can start to see these really start to separate. You're starting to get an appreciable effect, which I think is really, really interesting. And that's a little bit to do with this is very much to do with the transient sort of response of the lower emissions versus the higher emissions. So it does make sense, but it is interesting that you're taking up less carbon, but you are getting a larger cooling. And needless to say, over land, the cooling is larger than over the ocean. Okay, so now I'm going to go towards looking a little bit at the ocean acidification changes. And so what you can see here are the changes of the surface pH, 2020 to 2100, changes in pH, and what you can see is RCP 2.6, we see a decrease from the present day going down, and again 8.5, very, very large changes. And what you can see very similar to global temperature is you actually get a much larger increase or an offsetting of alkalinity of pH under lower emissions, higher emissions. In other words, it's more effective to add alkalinity under low emissions than high emissions. Again, this is the global mean. It doesn't really matter where you put it, which is really interesting. Again, the alkalinity was put in different places, and again, it made no difference, which again is really, really interesting. And so there's a little bit of small deviation, but it's almost similar. If you unpack that a little bit, there's a little bit of difference, but it's not much. And the reason behind that is actually important, and I'll come back to this at the end. And the reason is because you can think of ocean acidification as the difference between alkalinity and dissolved inorganic carbon. And under high emissions, dissolved inorganic carbon is going to go up. The ocean's going to take up more carbon, therefore this term's going to be bigger. So therefore, for a given change in alkalinity, you're always going to get a bigger change when you have less DIC in the ocean. So what that's really highlighting is the state dependence of doing alkalinity injection or addition. So now I'm going to move to aragonite. How much time do I have? How am I going for time? Awesome. All right, so this is aragonite. So this in some ways is reflecting the changes in the ocean chemistry, but it's also adding some dependence on temperature. So what you can see, and this is through Mucci's constant here, and you can think of aragonite as essentially a proxy for carbonate ion concentration, or we can actually think of it the other way around, right? So what happens here is you get almost, so what we're looking at in some ways are the pH changes, but we're adding some small dependence on temperature as part of this. And aragonite's really important because most corals in the tropics use aragonite as their primary form of calcium carbonate. So what you can see here is you see a bit, so again, you see a bit more of a dependence on where you add alkalinity, which reflects the gradient in temperature. But again, just like pH, we get larger changes under low emissions for the same reason I previously said, and smaller offsetting or smaller changes under higher emissions. And what's interesting too is that by the time we've reached these large changes, and in the previous slide, by the time we've reached these kind of changes at the end of the century, you know, the small kickback you get, the small sort of changes in ocean acidification, they're just so small, they're almost insignificant. And if you start to look at some of the thresholds and what we know about the systems, especially places in Milne Bay and places where you have natural CO2 sinks, the reality is you'd be very hard pressed to, under higher emissions, to be able to justify sort of the effects on both temperature but also on ocean acidification under the high emissions pathways. I showed you that. Again, I want to come back to the point that globally the things look fairly invariant to where it goes, but actually spatially there is quite a lot going on. And what's happening here in this plot is this is the global addition, this is the subtropics, the subpolar and the tropical ocean. And what I've plotted over here is essentially the red line is where aragonite saturation state is equal to 3, and that's often considered a nice place where corals transition from good conditions to poor conditions. So in other words, if in the future, in the future we expect that to constrict, the area for corals will get smaller going into the future. So if we're doing this right, the area for corals will increase. And that's just what we see. The black line is the 2.6 scenario with alkalinity addition. But what you can start to see is some of the changes are very dependent on where you add your alkalinity. You can see if you just add it in the tropics, if you're worried about tropical corals and you just want to put it in the tropics, you can start to see that you're getting very, very, very large changes. And what's interesting too, even in the global case here, we can offset the changes in the pre-industrial. In the previous slide, we saw we can kind of offset these are the changes from 2020. We in fact can actually reverse what we've seen in the pre-industrial. But what happens too, globally can reverse it, but we can also start to see changes in or values of ocean chemistry that were much larger than we found in the pre-industrial. So we have no idea how marine organisms may respond to that increase. So we offset the changes since the pre-industrial to even further. So it's an open question. What does that actually do to marine systems? Okay. So I'm going to come to the conclusions, and if I've got a moment, I'll just end with a couple of thoughts. As I said, the global changes are almost invariant to the location. I've said that. Despite the fact you take up less carbon under high emissions, you do see larger cooling and larger changes in ocean acidification under low emissions, and there's good reasons for that. So what does that mean? That talks about, it really goes to the heart of state estimation. It means that ocean alkaline, ocean liming, if you will, is more efficient under low emissions than high emissions. That's a really important point. You have to think about that. It's really important. It means that more AOA would be required to have the same impact under high emissions. That means that actually, as an option, ocean liming may not be actually something we have on the card forever. There's probably a window where doing, AOA is going to give some good results. It may have some good impacts in terms of temperature, offsetting acidification, but you would be very, very hard pressed to be starting this under a high emission pathway in the second half of the century and be able to justify the costs of doing that. So actually, that's something we haven't talked enough about at this meeting, the fact that not all options are on the table forever. And as I said, when you start to do this stuff, you can look at the global numbers. We talk about a 1.5 degree as a global change, but the devil's in the details. We need to look regionally. We need to think about ecosystems. We need to think about food security and a bunch of other things, of course, that we've touched on in the meeting. So this is my little grandstand for a second. Where, in my opinion, does some of this work need to go today? We've done some of this work. This is not the first study. It builds upon some great work. Where do I think it needs to go? So I think we have this carbon dioxide removal into comparison experiment that colleagues and I have set up, and that's now an endorsed MIP, and we'll have an experiment that looks at ocean alkalinity addition, and we'll start to look at what sort of is the difference between the models. How much consistency between this model and other models is important. I think the other question of reverse acidification is a critical question. It's a question both biologically, if you start to change the chemistry to conditions the corals haven't seen for tens of thousands of years or never seen, how will they respond? And equally, if we push the alkalinity up to such a high level, we may get into a situation where we get spontaneous precipitation of calcium carbonate out of the ocean, and that's a disaster to happen. And I think to that end, I think this is in fact just RCP 8.5 under the pH changes at the end of the century. And what I wanted to show you here, this is from an eddy resolving model. And traditionally when we look at the changes under the RCPs of pH, we see a quite homogeneous view. When you start to resolve the mesoscale, you can start to see all this convergent and divergent flow that's consistent with eddies. So the reality is we need to start going to eddies that resolve the dynamics better to start to understand how the changes would play out. And finally, this is alkalinity. We've just added alkalinity. The reality is that we're going to source our alkalinity from olivine, from a bunch of other things. There's other things in them. There's iron. There's a whole bunch of things in there. And we have to start thinking about what that means. So then we start to get to a situation where if we're doing those simulations, it's not just the abiotic ocean response, it's abiotic plus biotic response. And we need to know how that pathway or how that'll play out. Thanks.